Good morning. Happy Friday. Okay, so let's move to the problem where we left off on Monday. So we have the town of Gatesville, and it has been directed to upgrade its primary treatment plant to a secondary treatment plant, and you're told that it must meet an effluent standard of 20 milligrams per liter of BOD and 20 milligrams per liter of suspended solids. A completely mixed activated sludge system will be used. There's multiple systems, as I mentioned. The only one that we will look at is this completely mixed system. If you're interested in looking at wastewater treatment in much more detail, Dr. Safferman from Biosystems Engineering offers a course in the spring on wastewater treatment. If you can't find it on the schedule under BE, let me know and I'll help you out there. He and I used to, when we developed it together, and we team taught it for a number of years. And then he continued it on when I went on sabbatical, and he's been teaching it. So there's that course. It can be used as a technical elective in the environmental program. So just wanted to mention that. So getting back to this problem, we're going to assume that the BOD of the suspended solids is 63% of the suspended solids concentration. So take total suspended solids concentration. The BOD associated with these suspended solids is 63% of that. And you're initially asked to calculate the required volume of the aeration tank. And got a number of parameters. These are experimentally determined. So we have a situation here where we have a flow rate. So we're given a flow rate here. And we have a soluble BOD. And remember, when we're looking at biological treatment, we're focused on removal of soluble BOD. And you're told that the soluble BOD from the so we've got the primary treatment, the effluent from primary has 84 milligrams per liter of BOD5. I am going to add a couple slides. I meant to do this before class and I spaced out. So let's think about this in terms of a mass balance first. So we have primary treatment. And we have the effluent from that. That effluent from the primary becomes the influent to the aeration tank. So we're adding oxygen to that aeration tank. The effluent from that goes into a secondary tank. This is our secondary clarifier. We have effluent from that, and we'll use S sub E to note the effluent. The sludge from that, some portion of that is recycled back to the aeration tank. So we need to reuse the microorganisms. So this is our flow rate for the return activated sludge. And some of that is wasted. So for those of you that may have been spending COVID baking and you make sourdough, when you feed the sourdough, you have to feed it each week, and there's some portion that you typically will waste that you no longer, and that's the discard, that you're just producing too much of it. So you're told that this is 84 milligrams per liter. You're told that the effluent is 20 milligrams per liter, and that's our BOD5. and 20 milligrams per liter suspended solids. We need to draw a system boundary around here. And what we're going to do is we'll draw the system boundary around this entire process. So when we're looking at flows, we have the flow in from the primary tank, we have a flow out, and we have a flow from the waste activated sludge. Notice our return activated sludge flow rate is within the system boundary. So when we initially look at that mass balance, we don't include that in the mass balance equation. And we'll remember that the BUD 5 of the suspended solids is 63% of the suspended solids concentration. And we're looking for the volume. Just in terms of other kind of common language, we refer to the suspension of microorganisms in the aeration tank as mixed liquor.
So that BOD5 of suspended solids being 63% of the suspended solids, is that on top of the 20 milligrams per liter BOD5 you already have?
No. So this is the total BOD. So what we need to do to design is we're designing the entire system based on soluble BOD. So this 20 is the total. Okay. So if we look at let's just think of it as a mass balance on our solids. Or on our BOD leaving. So if we just look at BOD leaving the tank, we have soluble BOD, and then we have BOD attached or sorbed to the suspended solids. Okay, that's associated with the suspended solids. So we have 2, and this 20 is the total. So to calculate our soluble BOD, so this is the soluble BOD in the effluent. This is equal to the 20 milligrams per liter minus the 0.63 times 20. So this is the total. This is associated with suspended solids. And that is equal to 7.4 milligrams per liter. So this is S sub E. This here was given as the soluble BOD. So S sub 0 is soluble BOD. Does that make sense?
Yes, thank you.
There are a number of equations that I am going to introduce. I'm not going to derive the equations. I will place, and think where, I'll let you know in the email kind of which folder to put it in, but I will give you Chapter 11 of Principles of Environmental Engineering and Science. The textbook has multiple chapters on wastewater. We don't have time to go into all of that material. So Chapter 11 is the wastewater chapter from Principles of Environmental Engineering and Science. That will give you kind of an overview of wastewater treatment. And if you want to derive the equations, it goes through the derivations of many of these equations. Now, we can estimate the mean cell residence times. And when we're looking at these designs, one of the parameters that we use for the design is this mean cell residence time. And if you think about this, okay, we're recycling microorganisms. Kind of think about that as it represents how long a microorganism would reside in this. It's just going to keep getting recycled around. So it's not the hydraulic detention time. It's focused on the microorganisms itself. And the equation that we use for this is that S sub E is equal to K sub S plus, times 1 plus KD times the mean cell residence time divided by the residence time times mu sub m minus KD minus 1. Now, back in the slide that really with all of the tables, it goes through all of these parameters, but this is the half saturation constant. It's based on, if you look at a growth rate, it's based on the growth rate as a function of the substrate concentration. And basically what you get if you look at the growth rate as a function of concentration of the substrate, you get a curve that looks like this. And so the half saturation constant is that concentration associated with half the maximum growth. This mu sub m is the maximum specific growth rate constant. K sub d is an endogenous decay constant, so that is related to the rate at which the microorganisms are dying. And then we'll use it later, y is a yield coefficient. Y isn't in this equation here. So if we substitute in here, we have 7.4 equals, and these are the equations that you're given from pilot studies and empirical studies. It's 100 milligrams per liter times, and this is a plus, I apologize, 1 plus 0.05 times the mean cell residence time, that's what we're looking for, divided by the mean cell residence time times 2.5, 2.5 plus 0.05 minus 1. Okay. So it's a multiplication of this time minus 1, and that is equal to 8.2 days. Typically, for a completely mixed system, the equations are in the book. The equations are also in chapter 11, which, as I mentioned, I will post. And your mean cell residence times for a completely mixed system typically range from 4 to 15 days. So this is well within that range. The mixed liquor, volatile suspended solids. So there's two sets of terms. There's an X term and an X bar, X prime, sorry. The X terms pertain to volatile suspended solids. The X prime terms pertain to suspended solids. The difference, suspended solids includes inorganic matter. Volatile suspended solids is an attempt to quantify the concentration of the microorganisms. So this is approximately equal to the mass of microorganisms in the system. So let's assume a MLSS of 3,000 milligrams per liter. And typical ranges are 3,000 to 6,000 milligrams per liter for mixed liquor suspended solids. So that means that gives us this value. So this pertains, this is X prime. We need to know X, and X is typically about 0.7 times X prime. It's about 70%. So there's about 30% inorganic matter in this mixed liquor. So we'll start with 3,000. We'll see if that is appropriate. We can then use some, giving you equations, as I mentioned. I'm not deriving them. Chapter 11 does go through a derivation of the problem, of all of these equations. So X is equal to the mean cell residence time times the yield coefficient times the difference between S sub 0 and S sub E divided by the detention time plus 1 plus KD times the mean cell residence time. So if we make this assumption here, we start with the 3,000. So our value of X, so our volatile suspended solids concentration, this is our MLVSS, this is our MLSS. So this is our mixed liquor suspended solids right here, and our mixed liquor volatile suspended solids here. And if we substitute into this equation here, 2100 is equal to the 8.2 that we calculated. Y is the yield coefficient that was given as 0.6. 84 milligrams per liter is the soluble BOD entering. 7.4 is the soluble BOD leaving and think of the system as the aeration tank and the clarifier, divided by the detention time times 1 plus 0.05 times 8.2, and the detention time is equal to 3.05 hours or 0.127 days. So notice your hydraulic detention time, sorry, I changed notation. TD is equivalent to T naught. Sorry, I should not have done that. Thanks for catching it. So notice this is much less, okay? Orders of magnitude, almost an order of magnitude less. Actually, it is more than an order of magnitude less than the mean cell residence time. To get the volume, that is just our flow rate times the detention time, equation we've used a gazillion times, and that is the 0.15 meters cubed per second times, I use 0.17 days times 86,400 seconds per day, and that is equal to about 1,600 cubic meters. So this is the volume of the aeration tank. It does not include the volume of the sedimentation tank. We have to calculate that separately. Questions about this so far?
Yeah, just conceptually, like what should I be thinking for the difference between mean cell residence time and detention time?
Okay, so mean cell residence time, if you could hatch a ride on a bacterium, it's how many times you're going to go around in the system. If you could hitch a ride on a water molecule, that's your detention time. So your water molecules your water is flowing through much faster. You're not recycling. Think of it as you're not recycling water. You're recycling these microorganisms. And if that makes sense, it's kind of how long you're residing that mass of microorganisms, because the microorganisms are flowing backwards, and you're continually recycling microorganisms around and around and around and around. So they stay in the system a lot longer. So on average, they're kind of staying in the system, that mass staying in the system for 8 days. On the water, on the other hand, we're sizing this based on the water, and that's only staying in on the order of about 3 hours. Does that help?
Definitely. Thank you.
It's a hard concept, and actually, I'm not even going to give you a problem to solve on wastewater like this. It gets really complicated. I partly do it because I want you to see the coupling of that we're doing a mass balance for the substrate, the food, but we're also doing a mass balance for the microorganisms. And those mass balances are coupled by all of these constants that we use to describe the relationship between the microorganisms and the food. So we're describing how rapidly the microorganisms are growing based on the amount of substrate that's available. You'll have a few much simpler problems to do that are much more based on just the mass balance without having to go into all of this detail. I'm not going to give you any book problems where you actually have to go through all of these. I might ask you an essay type problem to give you kind of think about what's happening, but I'm not going to actually have you do all the calculations. So if you can kind of follow in terms of conceptually what's happening, don't worry so much about the mathematics. But I think it's important that you at least see how we couple these two systems. Now, the other thing that we use to design these plants is what's referred to as a food to microorganism ratio. And kind of think about this conceptually. So food or substrate, that's the BOD. Okay. The soluble BOD is our food. So that's your S. And your microorganisms, that's your X, your mixed liquor volatile suspended solids. Now, if you have too much food, what happens? You give your microorganisms too much food, what's going to happen? You go to Thanksgiving dinner, and there's always too much food, right? So what happens?
Are they gonna like get tired or like stop eating?
Yeah, they're going to stop eating, and and absolutely right in the chat, you've got leftovers. Might fall asleep. Yeah, I'm going to fall asleep, but that says tryptophan in the turkey. So if we have too much food, we're going to have leftovers. What does that mean in this system?
You have suspended solid, or you have stuff escaping the system.
Exactly, you have stuff escaping the system. So now we've got a high effluent BOD. If you have too little food, you asked all your relatives to bring over some food and 3/4 of them forgot. So now what happens?
You're starving them.
You're starving them, exactly. I forget to feed my little yeast for my sourdough. I starve them. So then what happens?
They die, and you end up with a high effluent BOD.
So now my microorganisms die. I've got very unhappy microorganisms. Okay, so think of it this way. So we want to balance the food to microorganism ratio so that we neither have lots of leftovers and sleepy microorganisms or starving microorganisms. And typically for a completely mixed reactor, we want this ratio to be about 2 to 0.4. And the ratio is determined as it's our flow rate entering times the soluble BOD concentration divided by the volume of the reactor times my mixed liquor suspended solids concentration. And that is equal to 0.31. So that is right within the range. So think this is your Q times your influent BOD divided by the volume times your mixed liquor suspended solids concentration. Now, the next thing we need to think about is kind of going back to our diagram here. We need to think about how much of this suspension of microorganisms do we need to waste? And we can think about that here as we need a flow rate. Okay, so let's first do that here. So we have Q waste is equal to V sub X over the hydraulic, that mean cell residence time times the VSS in the recycle line. So this is our VSS in the aeration tank. And this is our VSS in the return activated sludge line. Now you were given or stated that to assume that X prime is equal to 10,000 milligrams per liter based on pilot plant data. Okay, so that's the concentration in the sludge from the secondary tank. So then X, this is XR, XR, the VSS concentration is 10,000 divided by 1.7. Actually, it's just XR is equal to, there's a rounding error. I'm just going to do it this way, times 0.7, because we said it was 0.7, and that's 7,000 milligrams per liter. I have it written as the inverse, but there's a rounding error, so let's just write it this way. So then QW, our waste flow rate, is the volume of the reactor times 2,100 milligrams per liter, the VSS in the aeration tank, divided by 8.2 days, and I apologize for all these lines, times 7,000 milligrams per liter, and that is 87 meters cubed per day. So thinking of the system Here's the secondary clarifier. The flow entering that secondary clarifier is Q plus Q sub R. We have Q leaving here and the VSS in our effluent. We have Q sub R, and then we have Q sub W. We've written the system boundary such that this Q sub R is within the Q sub R is here, okay? So we've written it here where we have a flow rate here entering. We have Q sub R that's being recycled, and we have QW. And then we have all the X terms that are associated with that. So we can write a mass balance that Q plus QR. So we're using the VSS. So this enters minus QR times X prime plus QW X R prime minus Q R X A. And this is equal to 0. We've got Q sub R leaving. So notice we've only got one term entering. So this is our one positive term entering is right here. We have Q leaving here. We have QR leaving. We have QW leaving, and we have QE leaving here. We're going to assume that this is approximately equal to 0 because it's small compared to the other terms. And if we substitute here, and I'm not going to go through the substitutions, Q sub R is equal to 0.112 meters cubed per second. And Q sub R over Q in the plant is equal to 0.112 over 0.15, and that's 0.75. That is 75% of your flow that is actually recycled. So what is entering here is 1.75 times. So this term here, this X prime, is what's entering from the aeration tank. The X prime R's is what's leaving the secondary clarifier as sludge, and X sub E is what's leaving the clarifier as effluent. And from that, we can calculate this recycle ratio. I know that this is a lot of math. And
just that last Q sub R that you have in there that you canceled out to be approximately 0.
This one right here. Oh, I'm sorry. This is not it.
Q sub E.
You're right. This should be Q sub
Okay.
E. Yeah, thank you. Get rid of some of those lines. The problem actually asked to estimate the mass of sludge to be wasted. I think I'm just going to stop here with this recycle. Since I'm not going to ask you to do this to go any further. I think conceptually, hopefully you've got a sense conceptually of what's happening here. Okay. In terms of the mass of sludge to be wasted, I'm just going to write this in words and we'll leave it at that. Okay. So the mass to be wasted, we need to look at the sludge production. This is equal to the increase in MLSS. We use MLSS, not MLVSS, because when we're designing the subsequent reactors to treat that sludge, we need to take into account the entire mass. And that's minus the suspended solids in the effluent. So this has to do with growth. So this term here actually includes an observed growth rate constant. And then this is just the suspended solids in the effluent. So I think I'm just going to leave it here. Conceptually, hopefully you have some sense of what's happening in the system, how water is flowing in the system, and how we're recycling these microorganisms. So we're actually recycling. This flow rate is significant. And as I mentioned, it can be anywhere. It can be 25% to even greater than 100%. So that this clarifier is often quite large compared to our total flow. I'm going to talk really briefly about tertiary treatment. We've talked about secondary treatments. We've gone through primary, second, and secondary. So secondary, we said, was soluble BOD. In the case where we need to either remove more suspended solids, remove nutrients, or we're reclaiming water, we then move to advanced or tertiary treatment. We're actually going to look at some of these processes now. I normally do much of these processes earlier, but I decided to just incorporate both the water treatment aspect and the wastewater treatment aspect together. So we've already talked about coagulation. This is essentially the same thing. In this case, for instance, we're adding ferric chloride. We want that to react with the phosphate in the water. We produce ferric phosphate, which is extremely insoluble, and we precipitate that out. So typically, this is added at the end of the aeration tank before secondary clarification. Granular media filtration is, we're looking at removing of suspended solids. East Lansing plant uses both chemical precipitation and they use granular media filtration. We can use membrane filtration, and here is if we need a high quality wastewater. So for instance, in Singapore, they actually recycle and reuse their wastewater. They're water scarce. They actually purchase water from Malaysia. So they use membrane filtration to remove pharmaceuticals, personal care products, also remove viruses in this filtration system. We can use carbon adsorption to remove soluble organics and some inorganics, such as metals. And I didn't have it here. We can also use ion exchange. For instance, we can remove ammonium ions. We can remove nitrate, nitrite. And if you have a water softener, you know that is removing hardness. We often disinfect, and here what we're trying to do is to reduce pathogen levels to acceptable levels so that it doesn't cause problems in in the receiving body of water, and then we dechlorinate to reduce toxic effects. What we're seeing is the replacement of this with UV, because with UV, we don't need to dechlorinate. We irradiate that water and then we can discharge it. I'm going to end here. This is actually the Williamston wastewater treatment plant, which we would normally visit. We will have a virtual visit, but just to show you, these are the primary tanks. This is the grit room. There is actually an aerated grit chamber that you can't see here. These are the primary tanks. These are the aeration tanks. So water flows here to the aeration tanks, and then from there to the secondary clarifiers. And then from there to UV, and then it is discharged to the red cedar. Just to give you a sense of a one treatment plant. These are digesters. The sludge from the secondary clarifiers and from the primary tanks go into the digesters. Actually, it's a two-stage digester. So we'll end there, and happy to answer any questions you may have.